Okay, good morning, everyone. I hope you are doing all right and ready to learn some physics. So last class we started talking about conservation of energy, which is one of the basic physics we are learning in this semester. Other two were kinematic, kinematic equation and laws of motion. So we covered the kinematic equations or kinematics, and then we finished the laws of motion, and then we moved towards the work and energy and talked about conservation of energy after defining kinetic and potential energies, and learn how to use conservation of energy to solve any problems. Okay, any problem, not just one problem, but any problems. So that's what our focus is, and that's what we talked. So in that process, we said, okay, we want to first label three things after we sketch the situation. So for example, in this case, what's happening, the roller coaster car is going in something like this loop, okay? So it's starting from here means that's the initial, that's obvious, and it's asking us to find what speed does the car reaches to the top of the loop. So top of the loop is here. So that means this is going to be final. So last class, we looked at example where we used a reference line either at the initial position or at the final position, or the reference line passing through either the initial position or the final position. Here in this example, see the measurements are given from these points. So it makes sense, it makes more sense to actually use this as a reference. So this is an example where we are not using initial or final point for the reference line. Okay, so this is reference line. So once we have labeled these three things, what do? We note down the relevant quantities because conservation of energy is final energy is equal to initial energy, and this total final energy can be written in terms of sum of the kinetic and potential energy when there are no non-conservative, like let's say when there is no friction or other form of energy is present. So final kinetic energy plus final potential energy is equal to, we repeat the same thing, initial kinetic energy plus initial potential energy. And to be more clear, we can expand this by using the definition of kinetic energy. So kinetic energy is half times mass times velocity squared. That's the basic formula for kinetic energy. So since we're talking about final here, so we need to stick this final subscript in the speed because final speed gives us final kinetic energy. And we do the same thing for potential energy. This is definition of potential energy, where y is vertical position. If it is final position, then we can write that as a yf. And we just copy this to the other side by replacing final by initial. So we can see here, the conservation of energy involves speed and positions. No force, no acceleration, and so on. So because of that, what we need is these things. Let's see what are the things we know out of these, okay? So in this case, mass is given and written right there. So we can, we can see that. So I'm not copying that. And looks like in this equation, see the mass is in each of the terms, so that means mass cancel. So when there is no friction, mass does not matter, mass cancels, okay? Whether you have this big car or small car, the result gonna be same. So it's starting from here. So initial, so this is gonna be initial position, yi. So yi is 40 meter, and initial speed is 0 because it's just about to roll down. That's what it says, but that means it is not already rolling down, means it starts from the rest, right? And let's move to the final side here, final position. So our reference line is here, final is here, so the final position is this, 20 meter. And then final speed, and that's what we want to know, okay? So to properly do it, you want to write all these. Here I already wrote it, so I'm going to just copy this last one here. And from here we can tell the BI is 0. That means this is 0. And we are looking for this, so that means we want to push this to the other side. So that is half mvf square is mgyi, and this is positive in this side. When it moves to the other side, becomes negative. So mass cancels, giving us bf square. So 2, let's move this 2 to the other side. So 2gyi, and since you know, it's we have to multiply both terms here. Oh, 2gyi, and this is yf, isn't it? Yes, this is yf. Okay. So now bf is square root of these. There is 2g, 2g. If you do not want to multiply same thing twice, you can factor this out and just write something like that, and looks neat and clean. Okay. So all these numbers are known. So that means we should be able to calculate speed, and the final number is given here. Okay. So just a review of using conservation of energy. So far we've been avoiding friction. We are saying, okay, let's say friction is negligible. Friction is negligible. But in real life, there is always friction. So we also need to learn how to include friction. Okay, that's what we're gonna do next. But before that, I have another slide here that does the similar problem here. This skateboarder is rolling down like that, and we want to find speed over there, okay? So this example is done. And when we choose reference over here, down here, this becomes initial position, right? So that's why that is there. And final position is 0 because we are choosing reference right at the final point. And initial velocity is 0 because starts rolling down from there, and we want to find final speed. Very similar. Process is similar. As you can see, you label those, you note them down, and then you write the formula and set the zeros and solve for the things that you are looking for. And over here, mass cancels as well. So this is fully done in the note. Okay. So in this case, again, you are just solving for BF. Oh, this equal sign shouldn't be there. We do not want to keep writing equal sign. Okay, so yes, it shouldn't have been there. Typo. Okay, so now let's learn how to include friction and solve problem using energy idea. Okay. So for example, let's say this kid is sliding and there is friction. And sliding, so friction is kinetic friction force. We know it acts in the opposite direction of motion, right? And when one surface slides over another surface, what happens? The friction is doing work because friction force is there, displacement is there, means there is work. And that work done transfers the energy from system to the outside. In this case, it goes in the air, for example, right? It becomes warm and that energy gets dissipated in the environment. Some may go in the slide, some may go in the in the air. So that energy does not go providing kinetic energy for this kid while coming down. So we know if friction is negligible, what happens? The speed with which this kid will arrive gonna be larger than in real situation where there is friction. So it slows down to the kid. Okay, so kid does not arrive with as fast speed as it would if there was no friction, right? So, so friction has this tendency of taking energy from this object out because usually the friction does negative work, means the energy gets transferred from system to the another thing. So we need to keep track of that. So if we were to say, okay, kinetic energy and potential energy as our mechanical energy, so there is one more energy we need to include. So until now, total mechanical energy before and after were equal. Kinetic plus potential is mechanical, right? So they were equal. So that's what we used. Now, when there is friction, what happens? We need to use that thermal energy as well. Okay. So total mechanical energy before and after not going to be equal. Okay. But we also have thermal energy, and that's what I'm including here. So at the beginning, this kid has potential energy. Kid is not moving at the beginning. So all energy this kid has is because of this initial position over there. Okay, that initial position over here. So all energy is just potential energy, actually. Kinetic energy is zero. Now, at the end, what happens? All the energy is kinetic energy. But this kinetic energy not going to be equal to this potential energy because some of the energy goes out of the kid, kinetic energy of the kid, and that's what the thermal energy is. If we add that thermal energy back to the final, then total is still equal because total energy remains always same. That's what the conservation of energy means. So if we miss something, then it's not going to be equal. So for example, here we miss the thermal energy. Because of that, they were not equal. See the sign here, not equal sign, right? So once we include that thermal energy, now the total energy after and total energy before are now equal. Remember, when kid is not sliding, there is no thermal energy. So that's why we don't need to write thermal energy here. Okay. So we don't need that thermal energy. But when kid is sliding, right? So that's when this thermal energy arises. So if we were to calculate thermal energy, how do we do? It is the product or it is the result of friction force doing the work. So that means we need to just calculate the work done by friction force. And non-conservative force we are using here is basically the friction force here, okay? So in general, remember we write work done as a W. So for non-conservative force, we can say this. So this we can replace. So they are equivalent. So whatever work this non-conservative force or the friction force does, that is thermal energy. So they have equal value. So we can just substitute for that and write equation something like this. Okay. So here this E is not total energy. This is mechanical energy, by the way. Okay. I just use that notation uppercase E that we've been using for kinetic plus potential, right? So mechanical energy means kinetic plus potential. Okay, so that's what that is. So see, after means final, right? So final mechanical energy plus thermal energy is equal to initial energy. Or if you can also put this in this side, but in that case, you have to put negative sign over there. Okay. Because you need to subtract that much from initial to get final. So this can be rearranged. And remember, the work done by non-conservative force, they are often negative. So we can rearrange and write something like this, where change in energy means final minus initial, right? So that's what that is. And that's what we are doing here. Bring this to this side and bring this to that side. And this actually is always kind of negative for our purpose here. So the sign takes care of itself. So now all we need to do is remember this, or we can say, okay, we can write in terms of kinetic and potential energy that we've been doing, but it's going to be change in kinetic energy and change in potential energy. So if I were to write this fully down, what's going to happen? This is going to be final minus initial is the change in kinetic. Okay. And then plus final potential minus initial potential. That's the change in potential. So basically, we're going to be writing that, or even better, when we are writing in terms of position and speed, we need to expand that and write something like this. So this is final kinetic energy, this is initial kinetic energy, so the difference is change, right? So that's for kinetic, and we can do the same thing for potential. So now, see, there are these four terms here. That's what used to be before, but we have one extra because of the presence of the friction force. Okay. So now we have five terms. So over there, ooh, hard to get there. Over there used to be four. Now it's just rearranged. So final minus initial when you bring this side, and this being initial, so final minus initial. So before that would have been 0 when there is no friction force, but now there is friction force, means we have that work done by non-conservative force. Okay, only that's the difference. Okay, so let's look at this example of the kid playing on the slide. So work done requires force and displacement, right? So that's what it's giving us. So in this case, friction force is given as a force itself, not the friction coefficient. But whenever friction coefficient is given, you can write friction force as product of friction coefficient and the normal force, right? But here, friction force itself is given, not the friction coefficient, okay? So I have sketched the situation here. Slide is 4 meters long. So key starts from here. So let's say that is initial. And key derives here. So that is final. So we can choose reference over here. Okay. So now, once we note them down, we want to write the position and speed and so on. So let's say initial position. What is initial position in this case? Given the situation, initial position, what is it? Can you type that on the chat, folks? Is it 2 meters or 4 meters? So I see one response there. It's 2 meter. So yes, it is a vertical position. So that means we need to look at it straight, not the sideways. Okay. So that is 2 meters. And what is initial speed? So key distance from here means 0 meter per second. And now let's look at the finals. Final position. What is final position here? So we are drawing reference line passing from the final position. So that means it is 0 final speed, and that's what we want to know. Okay. So we have other information as well because there is friction acting. So slide length matters in this case. So 4 meter long. So that is, let's say, displacement is 4 meter long. And force itself, friction force, is 75 Newton, and mass of the kid is also given. So let's write that down. Okay. So those are the things that we are given in this case. Now, since there is friction present, we use work done by non-conservative force is equal to change in kinetic energy plus change in potential energy. So if I were to expand this, this is going to be. So first, let's look at the work done by friction force here. So kid is sliding down. So to find the work done by a force, we need to draw FD diagram, right? So friction force is going to be up and displacement is down. So the angle between them is 180 degree. Oh, hard to read over there. So that means we can write this as FD cosine 180 degree. Okay. And change in kinetic energy means final kinetic energy minus initial kinetic energy. And change in potential energy means final potential energy minus initial potential energy. Let me get rid of those so that it becomes a little easy to see. Okay, so here I see YF is 0, VI is 0. So that means YF0 means this term is 0, VI0 means this term is 0. So we are left with these two terms on the right hand side. On the left hand side, what we have is cosine 180 degree, that is -1, and there is Fk times d. So we know both Fk and d. We already know them here, right? So we know everything on this side. And then on this side, we have half mvf square minus mgyi. So we are solving for BF, and that's what we are looking for, right? Here. So to find BF, we need to solve for this one. So we want to move this to this side. Since this is negative, it becomes positive on that side. So it becomes mgyi. And I'm copying that negative fk times d. And this is half mbf squared. You see here, the final kinetic energy is equal to the energy, the potential energy it had over there, which is mgyi, minus whatever energy it went out of the kid because of the friction present. Okay, and this negative sign represents exactly that. So it makes sense. So now let's solve for BF. So I need to bring this 2 here. So T is dividing everything. So it's going to go and multiply everything on that side. And M is multiplying BF squared. So that means it's going to go and divide. Okay. And so that means BF squared going to be 2 mgyi this, and we need to divide by m as well. Actually, I can just write it outside the parenthesis. That means it's dividing everything. Okay. So BF gonna be just under the square root. So I'm just switching side of everything. So that is same as also writing like this, just in case. Okay. Same thing. So that should give us this answer here. Okay. If friction wasn't present, then this would have been 0. This would be 0. So that means speed would be higher. But because of the friction, see, it's taking some energy out of that mechanical system. Okay. So that's how we use friction in the equation. Okay. So I had planned that one for last class. So that what we did so far is left over from last class. So now we're going to move to the elastic potential energy. So remember, when we have something like there, when we have something like this spring, when we stretch spring, there is spring force, right? So that means when we are stretching, we are doing work, or spring force is also doing work. So work done by this spring force is equal to the elastic potential energy, and that work done gets transferred to the elastic potential energy. So when we stretch the spring, what happens? Now it has energy. If I let it go, it's gonna jump. It's gonna provide some kinetic energy there, just like when we stretch a string on that bow, that gives the kinetic energy to the arrow. So we looked at one picture last class, okay? And that's not just for the spring and string. This can be used for example, even our bone can be compressed and stretched a little bit. Even the steel rods, they can be stretched and compressed. Compressed and stretched. Okay. So we have seen these when we talked about Hooke's law. So I'm just bringing this for your reminder. Okay. And Hooke's law, we wrote, that gives us spring force is spring constant . times this is stretch or compress on the spring or spring-like object. Okay, so that's what that is. Oh, that's supposed to go there. Animation moved a little bit further there. Okay. So how do we find work done by the spring force? So what happens is work done. So far we talked, the force was fixed, it was constant, but the spring force depends on stretch. So if it is stretched just little bit, the force is also little bit. And larger the stretch, larger the force, larger, larger, larger. Okay. The force keeps changing with the x. So force is not constant. So this is variable force. So how do we find work done by variable force? Okay. So we can still use the definition of work done. Okay. So before we do that, let's write the equation for the elastic potential energy. Remember how the work and the elastic potential energy are related, or work and potential energy are related? They have equal value with opposite sign, right? And that's what I'm writing here. This change in elastic potential energy is equal to negative of work done by that spring force. Okay. So what is work done by spring force? Force times displacement. So see, this negative sign just propagates from there. Okay. So how do we find work done here? See, this is product of force and displacement. So when we have product of two things, for example, we had a product of velocity and time, which gives us displacement. When we have that kind of situation, we said, okay, we can make velocity versus time graph and find the area under that, and that gives us displacement. So product of these two axes is the area, and physics tells us product of these two is displacement. Similarly, now this is product of two things, force and displacement, or change in length of the spring. And it says the product is either work done, okay, that product is work done. So to find work done, what we can do is we can make a plot, okay. So did I make a plot? Okay, here is my plot. So needs to be area under that plot. So based on this equation, we know this is going to be always a straight line. See, we are plotting that force and x, and they are related by Hooke's law, means they're going to be always a straight line. So it's never going to be something like that as long as it is within the elastic limit. So it's going to be always a straight line. So that means area under this always going to be a triangle. So we need to find just area of a triangle. Okay. So that's what we are doing here. Okay. And we know area of this triangle is half base times height. So if that base is, let's say, x1 or simply x, since there is only one x, we can just write x as well. The force is this. So this is force, right, at that point. And this is force, we know, also depends on k and x. So that means base gonna be x or x1, depending on what you like to denote with. But since there are no two values of x's, I will just be using the x, okay, rather than x1. So x here, and this is gonna be kx. So we are just looking at the length here, okay? So this is going to be base and kx is going to be height. So when we enter that, what happens here? Base is x, height is k times x, and half is already there. So we have k times x means half k x squared. So that gives me that. So that is the formula for elastic potential energy. And since it is x squared, whether it's stretched or compressed, which way it goes does not matter. Elastic potential energy turns out to be always positive based on this equation. K is always positive. X can be positive or negative, but when we square positive or negative, what happens? It is just positive. So that's why it's going to be always positive. Okay. So that's the elastic potential energy. So a typical spring can have a spring constant, something like this. Okay. And it says it's compressed by this much. Okay. So what is the elastic potential energy stored? Oh, I forgot to turn on clicker. So let me turn on clicker here. Okay, go ahead and do simple calculation here and choose a answer. And you have 2 minutes for this. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got. So we got mostly B, we got also C and D as well. Okay. So K here. And remember we use lowercase to denote spring constant is 200 Newton over meter. And the X in this case is 0.1 meter. So elastic potential energy. So we use uppercase U for the potential energy, any potential energy, and E subscript means elastic. So we learn about gravitational potential energy. That is because of the change in vertical position. Here it is elastic potential energy we just learned. Okay. Half K is 200 and x is 0.1, and it has to be squared. So this becomes 100 times 0.1 squared. So that is like 10 to the power negative 2 or 0.01. So when we multiply these two, we get 1. So it looks like, yes, B is correct answer, just like most of you did it. Okay. So it looks like those of you who chose 10 basically forgot to square it. And if you chose 2, probably you forgot to divide by half. Okay, so that's what happened. So a lot of toy, for example, toy guns and so on, they use this spring to launch a bullet or ball, something like that, right? So if you have something like that and you compress like that over there and let it go, what happens? It starts with some speed over there. So when you compress this, there is elastic potential energy, and when you let it go, that goes into the kinetic energy of the ball. Okay, so that is what the elastic potential energy is, and when we talked about elasticity, we said, okay, every matter is made up of either atoms or molecules, and there is a bond between them, and the bond acts like a spring. So that means when object, let's say, gets stretched, all these bonds get stretched like a spring, okay? And that's where the energy gets stored, okay? So let's look at the example of using conservation of energy where the spring is involved, okay? So in this case, what's happening? There is this spring and there is this a block, which is initially moving with some speed, okay? So now we have this spring mass system. There is spring and there is a mass. Mass is moving towards the spring and collides to the spring. And then what happens? Spring does work. And because of that, what happens? It slows down, and at certain time or at certain distance, it's gonna stop before it gets launched back, okay? And so I am showing that situation here, okay? So basically, I'm drawing in two places, but they are basically same thing, okay? So here is initial, and here is the final. That's what we are interested in, okay? And since the both drawing are basically equivalent thing, I'm just separating them to show, clearly. Basically, both of these are same line, and we can say, okay, that's our reference line. So in this case, what happens is the spring is not moving. It simply gets compressed. That's it. It's not moving from one place to another place. So spring does not have kinetic energy. Thing that's moving is block. So it has a speed, so it has kinetic energy. Okay. And how about gravitational potential energy? Now we need to look for two possible potential energies. One elastic, another one is gravitational. So which one is relevant when? When there is spring or string getting stretched or compressed, elastic potential energy is relevant. And when vertical position of the object is changing, then gravitational potential energy is relevant. Here, the height or the vertical position is same all the time. So if we choose reference, what happens is initial position in vertical, yes, initial vertical position yi is 0, and final vertical position is also 0 because it's not going up or coming down, right? It's just staying on that line, just sliding and pushes this, right? So we can write those things. So for example, vertical position, 0, initial vertical position, final vertical position is also 0 because the position in vertical reduction is not changing. And then now initial speed is given, which is 3 meter per second. How about final speed? Final speed, see here, when it arrives over here, it briefly stops. Just like when we throw something at maximum height, object stops, right? In vertical reduction. So the speed in vertical reduction becomes 0. Similarly, in this case, at maximum compression point, it's like a, object thrown in vertical reduction. Kind of similar situation. Over there, gravity is pulling it down, which is conservative force. Similarly, in this case, a spring is pushing it, right? So it's acting in opposite direction, just like when we throw something and when it is moving up, the force is down. Similarly here, when this thing starts touching here, when V is this direction, the force, spring force is in that direction. So situation is exactly similar. So at the maximum compression point, it's like a maximum vertical height, okay? So at that point, the final speed is gonna be 0. And after that, what happens? It's gonna start moving back. We're not talking about that. It says how far the spring compressed. So that's all we need, okay? So now, since there is spring involved, we also have X, the stretch or the compress on the spring. So initially the spring, what happens? So this is initial for the spring, okay? So right before this thing touches, it is moving with speed vi, and what's the spring stretch or compression in spring? It is neither stretched nor compressed. It's relaxed. We say, okay, spring is in equilibrium condition. So that means initial stretch or compress is 0 for the spring. And how about final? So it goes from here to here. So that is like a final stretch. Okay. So that means this value, whatever that is, that's what we want to find. Okay. That's what we want to find. So now let's use, so here we are, see the frictionless, it says, so we are neglecting friction. So we don't need to use work done by non-conservative is equal to change in kinetic plus change in potential energy. We don't need to write that, okay? We don't need to use that. Rather, we need to use this one here. Yes, total final, total initial means final kinetic plus final potential is equal to initial kinetic plus initial potential, just like before. But now there are two possible potential energies. And since the y zeros, if you decide to not write the gravitational potential energy, you are fine. But sometimes this height may also be changing. For example, let's say the spring was vertical and something drops on the spring and pushes the spring. In that case, what happens? The height is also changing, okay, of the mass. So that means gravitational potential energy is also changing. So in that case, you have to use it. So I'm gonna write it fully, and then later we're gonna plug in this as a 0. So that way those terms gonna be 0. Okay. So half mv f square. So only thing that's moving is this block. So this m is mass of the block, and which is given, and that I did not write, looks like, in the list. Okay. So that's half mvf square. And then potential energy, there are two possible potential energy. One, our good old gravitational potential energy, and then the one that we just learned about. Okay, so now we have three terms. And we have to copy all those on the left-hand side and replace final by initial. But a lot of things are 0 from the list we can see. Since the position in vertical reduction is not changing, what happens? Whatever this is, same is that. So we can say, okay, reference, by choosing reference line, we can make them 0. So they're going to be 0. Final speed is 0 at this moment here. So that means this also going to be 0. And initial compression on the spring is also 0. That means this term also going to be 0. So what are we left with then? This term here, half and this one here, half mvi square. So mass does not cancel, but half cancels here. Okay, we are solving for xf. So that means I need to bring the k on the other side. So other side, we are left with this mbi square, right? And then k comes here and divides. So that would be xf squared, but xf is just this square root of that, okay? So we know all these. And if you like, what you can do is you can pull this bi square out from the square root. So square root of bi square is just bi. So if you like, you can write something like this. So that makes mathematics a little simpler, but you don't have to, okay? And once you plug in these numbers, you should be able to get this as the answer, okay? So I realized that worksheet supposed to due last night, Tuesday, right? Usually that's what it happens, but I forgot. So it's due tonight, last worksheet. So I was planning to put the new worksheet on the slot, but I did not, because what happens is students sometimes upload their worksheet in wrong slot. So usually I try to avoid having two up at the same time. Sometimes it may happen. So the new worksheet is there in worksheet and feedback folder. Okay. So worksheet number 6 or 7, okay, new worksheet is there, conservation of energy. So that worksheet contains problem like we learned last time, so like calculating things, something like that. And there is also a question related to finding work done from course versus position graph, which we just talked here in this slide when we were calculating this, something like this, right? And third question is about spring and the mass. So we covered all those three ideas. So you should be able to now completely do that worksheet, okay, without, let's say, looking at any help. But as always, I'll be posting feedback a day before it's due, so you can look at and make corrections if needed. Oh, it was kind of done. Okay, so, and similar, this is similar to that worksheet I'm talking about. Okay, this problem is very similar to the worksheet. So this problem is also done in the note. As you can see, yi0, yf0, just like we did. And here, this is initially compressed. And once it pushes this skate border, what happens? It gets relaxed. So xi is non-zero, but xf is zero in this case. That's kind of opposite. Over there, the spring was compressed at the end, but here at the end, spring is relaxed because it starts from compressed position. So compressed spring is pushing the skate border. Okay. And the equation is similar to what we just wrote over here. See, 3 terms here and 3 terms here. Same idea. So once you understand one fully, okay, one problem fully, then basically it's the same process. Okay, so that's why I'm focusing on process, how to systematically solve problem. And when you do that on the worksheet, that's what I like to see. You want to show all the process, including initial, final position and reference and so on. Okay, it's like this. And then list the things, then write down the formula, and then solve for it. Okay, things that you are looking for. So all problems can be solved just like that. So if you do some sort of shortcut, then I'm not sure you understood full process. So in that case, I have to take some points off for that to remind you that you did not learn the process, or even if you did not show it to me. Okay. So that's how I grade. Hopefully you know by now if you've been checking your worksheet scores, okay? So now with that said, looks like it's a good time to take break. So after break, we're gonna move to power, okay? So I'll see you in 5 minutes. Okay, folks, welcome back from the break. So with energy behind, now let's talk about power. So in our daily life, we may, we may not differentiate between power and force or even energy. But we learned that force and energy, very different thingy. So energy arises when force does the work, right? And now what is power then? So power is related to force and energy, but it is not same. So it is how quickly the work is being done, how quickly energy is being transferred. That's what the power is. So for example, here there is a sports car and there is a regular car over there, right? So how do we tell which one is more powerful? Oh, sports, it must be powerful. Yes. Okay. So what happens? That if we drive a sports car versus regular car for the same distance, okay, in a similar road situation, then what happens? Energy spent by them is about the same. Okay. But if it is a sports car, what it means, we can arrive to the place quicker. So it's transferring that energy quickly. It can transfer energy quickly. So a sports car, for example, can go from 0 to 60 miles in 3 seconds, 4 seconds, right? Something like that. Or even quicker than that, 2 seconds, 1 second. Maybe not 1 second, but 2, 3, 4 seconds, right? But our regular car may take 8, 9, 10 seconds, okay? So although it may be transferring same amount of energy, but they are transferring at different rate. So that's the power, right? So for example, when I'm lifting something up, right? From here to all the way here, I'm lifting this mass. So I'm doing work. So when I do that work slowly, or lifting it slowly, so it takes longer to do the same amount of work compared to, let's say, when we go like this quick, okay? So when I'm doing this quickly, I am transferring that energy quickly, means I'm using more power, okay? So if you are, so this is small mass, so I can lift it quick. But if I try to lift some big mass like cows, I cannot lift cows that quick, okay? So my power is not enough. So how much power I can supply is kind of looks like limited, just like car. For example, you can keep pressing the gas pedal on a car. What happens? Regular car still takes a long time to reach that high speed, but sports car, they can go quickly. So anyway, so that's the difference between power and energy, or work. Work and energy, they are equivalent because doing work transfers the energy. Whatever amount of work is done, that gets transferred as energy. So work and energy are equivalent, but power is rate of transfer of energy, how quickly. So time comes in equation. So we denote power by using uppercase P, okay? And this is change in energy, so transfer of energy that is from the work done, right? So change in energy over time interval is the power. So this is the proper definition of power. But since work done and transfer of energy are equivalent, we can also write power in terms of work done, or even in terms of force, because the work done depends on force. So for example, where is that equation? So before that equation, let's talk about unit here. So energy has unit joule and has unit time, has unit second. So this is joule per second. So that's the unit of power, but we write that as a watt. So 1 joule per second, oh, now it's showing up. 1 joule per second is 1 watt. So when you have 100-watt light bulbs in your room, for example, what that means? It's changing 100 joules of energy into light and heat every seconds. That's what it means, 100-watt light bulb. So that's the joule per second. That many joules every second. It's transferring to different kind of energy. So what kind of energy is transferring to the light and heat? Is the electric energy. Okay. So it's converting electric energy into light and heat. Sometimes you may also hear little humming sound coming from the light bulbs. That's possible. So heat, light, sound, all these, other form of energies that may arise. So electric energy being transferred, but for what is not just for electric energy, it can be any kind of energy. Any kind of energy transferring every second is the watt. Okay, so that's the unit. So just like I was saying, we can write power in terms of force as well by using definition of work. Remember, work is F d cosine theta. For d, I am using delta x here and kind of writing there. Since they are all multiplying each other, I can write anywhere I like. So I'm doing this so that I can pair this two. So this is like displacement divided by time interval. And we learned that displacement divided by time interval is average velocity. So we can also write this equation something like this. But the basic formula for the power is this. This we are deriving from that, either this or that, depending on what we know or what we want. Okay. So that's the power, folks. So now I have a question for you related to power. And you have 2 minutes to answer this question. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So mostly B and C, mostly C. Okay, tie. Okay, how do we know that? Let's take a look here. So in this case, position is changing, vertical position is changing. So change in position for A is, I'm writing that as a delta Y, okay? So yes, I could write initial position 0, final position 10. So delta Y is 10 meters, okay? Final minus initial, 10 meter for student A, 10 meters. And time for student A is 8 seconds, T is 8 seconds, and for student B, it's a 20 meters. Maybe it's a good idea to put subscript A, B, and time interval for B is 16 seconds. Okay. Now, power is talking about mechanical power, means, that comes from change in kinetic and potential energy. So power is change in energy over time. Change in energy can be change in kinetic energy plus change in potential energy over the time interval. So in this case, change in kinetic energy, see, speed information is not there, so we can assume whatever the speed the particular student, a particular student starts at the bottom, also end up being with the same speed at the top, because that information is not there. So we can safely assume that. So the kinetic energy is not changing. Only the potential energy, which is gravitational potential energy in this case, there is no elastic potential energy involved, no string or spring attached, right? So that means it's going to be just mg delta y over time interval. So now, if we use that for A, power for A, what's going to happen? M is same for both, G is same for both. So this is going to be delta Y for A over time interval for A, right? And power for B is mg delta Y B and time interval for B. So mg is same for both of them. Now it simply depends on this ratio. And delta y over time interval, so if you divide 10 by 8, and over here you divide 20 by 16, right? So what happens? Both of them are basically same. So for example, if I divide PA by PB, power of A by power of B, let's write it down. mg delta y A over time interval for A, right? So that's power for A. I can divide that by power for B, which now fraction of fraction, so I can invert that fraction and write something like this. See, the mass and G, they being equal, they cancel, they become irrelevant. So they simply depends on the ratio of this. And ratio of both of these, they are basically same, so that's why they tie. And if I were to plug in actual number, let's see how does it look like. Delta YA is 8, oh, YA is 10 meter over 8 second. And here, this is 16 seconds over 20 meter. So when I do that, what should I get? I should get 1. So is this 1? 10 times 2. 8 times 2 is 16. So this 2 and 2 cancels, giving me 1. So power of A is power of B. Right. Oh. Power of A is power of B, right? So we can do that. But we don't have to go through all these. We can just look at power depends on the ratio. And ratio for both of them are same, because 10 over 8 is same as 20 over 16, right? So ratio is same, means power going to be same. So you can quickly answer this question even without going through all these, but that's the systematic way of comparing power, okay? When you have two objects or persons involved. Now, here is a problem directly related to what we just talked about. Can you do this problem and type answer on the chat? Okay. Everyone, please go ahead and do this problem. Are you working on it? I like to see number from everyone, please. Here we have a number and also include unit with your numbers. Okay, we have different number with units. Watts is the unit, yes. Number, is that correct? I don't know. So far I have two different numbers. Okay, now we have third number. Very close to second number. When we round, they are basically same. And we have now fourth number. Okay, now we have another number that matches with the last one. Now 16 is kind of becoming majority so far. Do I know the answer? I don't. So mass is 66 kilogram and value of G, let's use that as this. change in height is 16 meters, and the time interval is 66 seconds. Hey, 66 cancels. And this kilogram meter over second square is Newton, and this is meter. So the unit is Newton times meter, and there is second. So this is joule per second, which is watts, okay? Or simply watt. In terms of number, so the 66, oh, I use these clever numbers so that we can easily do that. So it looks like this is around 10. This is 16. 16 times 10 is 160. So in 2 sig fig, these numbers are 2 sig fig. So when we round, it looks like it's going to be 160 watts, okay, after rounding. But before rounding, yes, looks like it's going to be 156.8. Okay, so it looks like there was problem in rounding. Some of you missed the whole zero. That's totally different, right? So 157, if we had like 3 sig fig, then 157 would have been the better choice if we are working with 3 sig fig, but these are just 2 sig fig number. So that means we need to round to 2 sig fig. So that does not mean we round it to just 16. 16 and 160, they are very different, right? So that's that. Now I have another question for you. Excuse me. So here is another question. See, it says 30 miles per hour, 60 miles per hour. The speed is doubling. Here there is no information about the road going higher or lower. So that means delta y in this case is 0, but there is delta v, okay? Velocity is changing. So there is change in kinetic energy. So power is coming from change in kinetic energy, not the change in potential energy. So in our previous example, the power came from just a change in potential energy. Change in kinetic energy was 0. Now, in this example, what we have is change in kinetic energy, not the change in potential energy. Okay, with that said, I'll let you work on this. So it says miles per hour. So if you want to do it quicker, what you want to look is this is 30 versus 60. So speed doubled. Speed went from v to 2 times v. Okay. Yes, you can use this speed, but for that you have to convert that to meter per second. Okay. You can convert and find all the numbers, but you can also do, okay, it's just doubling. See if I can just come up with the answer with that. Okay. So with that said, I will let you work on that. Okay, let's do 30 more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. We got varieties. But there is majority in A. So T 2 seconds for 30. So 4 seconds for 60. Straightforward, isn't it? But is it? Okay. So A is incorrect answer. What is correct answer? Well, let's figure out. Okay. So in this case, power, we use same formula, change in energy over time interval, but change in energy comes from change in kinetic and change in potential energy over time interval. So this is 0. So it comes from change in kinetic energy, means it comes from half m. So kinetic energy changes because velocity changes. Okay. So I can write delta V squared over time interval. So in this case, power is same. So let's say car number 1 and car number 2, both of them have, oh, it's the same car, not even a car number 1 and 2, it's the same car, right? So it says, okay, the power output of the engine is independent of velocity and neglect air friction and air resistance. So that means power independent means power is fixed. So that means, of course, the mass is also fixed. So what's changing? Velocity changing, and to compensate. So this ratio has to remain same. Okay. So velocity change for this one is 30, and velocity change for another one is 60. So that means what's happening? Velocity change is doubling, right? So change in velocity is double for the second car. So that means when you double, say change in velocity double, when you square that, what do you get? You get 4. Double squared means you get 4. So that means the time interval also has to be 4 times larger to keep this thing same. So it's 4 times larger. So for this, it was 2 seconds. So 4 times larger of 2 seconds is 8 seconds. Okay. So what if it was like 90 miles per hour? Then this is 3 times more. Delta V is 3 times more. 3 times more squared means this would be 3 squared. So this is 9 times more. So time has to be 9 times more as well to keep the ratio same because power is same. So 9 times more means 9 times 2 is 18 seconds. So that's why when you are driving car, get into highway, now you are trying to reach that maximum speed, what happens? It takes longer and longer to get to higher and higher speed. Okay, so the 4 seconds would have been correct answer if this formula of kinetic energy was just delta V, not V squared. Because there is V squared, what happens? We need to square the things. So now, okay, Ramesh, looks like you're just talking. Show me the math. Yeah, we can do that. Just like we did for the, you know, these two climbers, one going through the, how much, 20 meters high versus 10 meters high, something like that, right? We compare that, we wrote the equation and we compared. So we can do the same thing, right? So situation one, power gonna be, let's say, half m delta v squared over time interval. And for situation number two, so these are gonna be different. So I'm putting subscript on them, okay? So P2 half m delta v2 squared over delta t2. So two different situations, but the power remains same. That's what it says. But power 1 and power 2 are same. That's what it says. Power output is independent of the velocity. So that means engine is, supplying same amount of power. So that means I can write this half m delta v1 squared over delta t1 equal to this one here, right? So half m delta v1, not 1, now 2, delta t2. See how the things that's not changing does not matter, they cancel. You see that? Things that does not change, they cancel. And now we want delta t2. So let's bring delta t2 over here. And delta t1. So I am bringing this on this side over here. So I am moving, oh, this should have been squared here, okay? So right hand side, I am left with delta v2 squared. And I am bringing this delta v1 squared on the bottom, switching the side, cross multiplication probably you may have heard. All right, delta v1 squared, okay? So this is ratio, so even if you don't convert the units gonna cancel. So what we have is when going from 0 to 30, 0 to 60, right? And this is 0 to 30. So change was 60 here, it has to be squared. Change is 30 here, has to be squared. And unit miles per hour, even if we don't convert, both of them gonna be same, so they're gonna cancel, okay? So now you see here, it's easier to see if we do something like this. If this ratio is squared, right? I can write that something like that. So this is 2 squared. 60, 30, 30, 60 divided by 30 is 2. 60 is double of 30, right? So that means this 2 and this square thingy is because of that square in the formula. You see that? So 2 square is 4. So this is 4. But that is the ratio. Now what is delta T2 then? 4 times delta T1. So delta T1 is 2. So that means it gives you 8 seconds. So that's how we systematically solve this problem. But you don't have to go all these trouble. You can just look at here. Hey, change in velocity was double. Double square is 4. So that means time for double speed is 4 times more. 4 times more. So for original it is 2 seconds. So 4 times more is 8 seconds. If it was 3 seconds, then 4 times more would be 4 times 3, 12 seconds, and so on. So anything you like to ask or add on this? Because We had quite a few mistakes here. So you need to pay attention to the equation. Is it in the equation, the quantity being talked is squared or just not squared? If it is squared, then you need to square the ratio, okay? Okay, let's move on then. So I don't have these things in my note, but it is from book, and this is section 7.8. So it is application in humans, okay? So what we taught applies to everything, of course, and we can talk, how this works in the human as well. Just like we said, energy we get is basically food energy. The OE here means other form. See, this is neither kinetic nor potential, and neither thermal or energy from the friction. So the book also uses these terms: thermal energy, kinetic energy, and potential energy. Everything else, it says other energies. So whatever food we eat, what happens? We may do workout. Okay. When you do workout, you consume that energy. So that energy get out from your system. So that's why it says negative and it says non-conservative. Okay. Work done by non-conservative force equivalent. And then there is this energy that goes on keeping your body warm. Okay. So that's the thermal energy. And if you eat more than what's needed for this, so yes, this one is minimum you need. Okay. The thermal energy is minimum you need. And then so that means if you are, let's say, sleeping all day, not moving around, not doing anything, not lifting anything, not running anything, not doing anything, that's the all energy you need to keep your weight constant. Okay. Now, of course, we walk around, so that means we do some work. We are moving our own body, we are lifting our body. Okay. So in that case, whatever you do extra, you need food for that. Okay. So those are the needed one to keep your weight constant. But if you eat more than that, and then what's going to happen? You're going to store any extra in the form of energy as a fat. Okay. So it converts that energy to a fat. Okay. And when you are totally deprived from food, then your body starts taking that storage from the fat and it converts. Okay. So for that to happen, you have to stay hungry for at least 24 hours. Okay. For this fat to burn at least 24 hours. Until up to 24 hours, if you're not eating, what's going to happen? It's going to just consuming food that you have eaten from before, because that goes in the blood, and there is triglyceride and so on, so those can be used as the energy. And once that is consumed, then what happens? It attacks to the stored fat. So that's why people can stay hungry or not eat, I should say, for long time. They do fasting for a long time. So I have seen people who survive just by drinking water for 28 days. I have seen with my own eyes. But I have read, when a person was put, by the way, that 28 days, that person was under the observation of the doctor, by the way. So they simply, give the water and that's all that's needed. They did not put glucose or anything like that. But I read news like there was a person, I think it was in England somewhere. Uh, that person went nearly 6 months or a year without eating and lost a lot of weight. Okay. And he was under the inside the hospital. He was in the hospital under, observation. So there wasn't much damage in terms of health-wise. He just lost the weight. What happened? He was bit, a person with a bit more fat. So the body started consuming fat after, I think, 2 or 3 days. It started consuming fat. Okay. So I don't have that kind of experience of staying hungry. So that's why you may see I'm not like a, okay. So oh, you cannot see me. So I can say, oh, I'm slim guy. Maybe you'll still believe, but I'm not that slim. So anyway, so that's how the energy that we spend, depends. And if we're talking about power, so if you are running versus walking, you are spending more, I mean, same energy, but quickly, right? If you are running for the same distance. But if you run same time, what happens? You can run for longer distance. So that means you are spending more energy and so on. So these things are in the book. If you are interested, I'm not going to be testing you for these, but I think many of you are life science major. So maybe it may be of interest to you. You want to look. And there are specific numbers that's also given in the book. Okay. And so how you are consuming energy and power in the body. So that thing is there just for record. So with that said, oh, it's 51 as well. So let's leave it here. And today I have Zoom hour. If you have question, you can come back and ask me question. If you have quick question, you can just stay behind and ask me. Okay. Otherwise, I'll see you next class.